Hello everyone, thank you for joining us at Coder Inquisition. So today's problem was actually very challenging to create a solution that wasn't brute force. By brute force we of course mean just for every value in the first array, and for every value in the second array, and in every value in the third array, sum them, and if they equal 0, then just increase your count by 1, we found a match. But that's very slow. In complexity terms, that's actually n to the third, which, while still in polynomial time, is very slow. So how do we create a faster solution? Well, if you looked at the hint videos, we offered 2 hints. The first was to try and sort the arrays, and try and do something more intelligent than just brute force to see if we can reduce the number of unnecessary checks that we're making. That alone can help you. I'm sure some of you found some very intelligent ways to go about it. But we want to talk about kind of what we recommended in the second hint video, if you watched it, and that's to actually don't use the array data structures as much. Actually turn these into a matrix, excuse me. So once again, this problem was extremely challenging, and if you didn't get to the solution I'm about to show you, don't feel bad about it. This was a hard problem. When I first encountered it, I didn't know what to do at first. So I'm just going to show you, and we're going to get into it. So what I did here is I actually constructed a matrix with the first 2. Now, the trick for sorting these is the second array I put up here, and this is sorted. And I actually sorted this one in reverse order, and this is the first array. So this gives me this matrix of values, and I left the third array as is. No sorting, no conversions to a matrix, or anything like that. So how does this help us? Well, it helps us like this. For the first element of this array is -1. So in this array, for every 1 we see, we're actually doing okay, because that means we found a match for every 1. So as you can see, being human beings, that's this one, and this one. So how do we search for those? I mean, we could just scan it, but is that really that much better than the brute force method? Well, no, not really. So here's the trick though. Do you see any patterns in this matrix? Go ahead if you want. Pause the video, see if you can see patterns that can help us search. Okay, so if you didn't pause the video, that's fine. If you did, I hope you found something. If not, I'll go over it right now. So if you notice, from any number in this matrix, the number directly below it is actually less than it, and the number to the right of it is actually greater than it. And, the reverse of that logic going other ways. So if we start at the first element 5, everything to the right of it is greater, everything lower than it is lower. So we're looking for 1, which is the negation of -1. Well, 1 is less than 5, so we can automatically conclude that none of the numbers to the right are going to be 1. Unless, of course, it's the number immediately, because you can get equivalent numbers, which isn't demonstrated in this matrix. But it can happen. That is an edge case. So we're trying to get to 1, we go down. Well, 3 is less than 1, it's not greater than 1, so we go down again. Then we find a 1. Yay. So we found 1 match. Now, there's a small edge case to catch here. Normally what you would do is you would actually immediately step to the right after finding a match, which does work, to cover the fact that there might be one here, but there also might be an equivalency here. So when you solve this, you actually want to do a quick array cast, so to speak, or just check in a line in layman's terms. So check down. So here we would just check 1 below it, and it's not 1, so we can actually just stop. If this was a 1, we'd keep checking until we encountered something that wasn't a 1, and that catches some of the edge cases. But seeing as that's not going to occur here, we're just going to step to the right and repeat the logic. So 1 is less than 2, so we go down. We reach another 1. We increment our count. And we check down. This isn't a 1, we go over. Well, 1 is less than 2, so we're going to go down once again. Oh, a 0. So 1 is going to be greater than 0, so we're going to step to the right. We found a 1. So We check down, nothing's there. We go to the right, 2. Well, we've reached the end of the matrix. And we're done. So the longest path you can ever take through this matrix is actually 2n. Okay? So what we have here, we've reduced the complexity. Can you see it? Originally, with the brute force method, we had O of n squared, or to the third, excuse me. This one, we have n, which is the size of each array, and then we actually have a maximum of 2n here being searched. So our complexity actually is reduced to O of 2 times n squared, which, if you know complexity theory, actually simplifies the n squared is said to dominate the multiplication by 2, and so we actually just get an n squared solution. And there you go. That's it. So as you can see, this was a very intelligent way of doing it. Restructuring data and then searching it in intelligent ways is something I think you can find valuable in a lot of your problems. And once again, this was not the most intuitive of problems. As far as interviews go, you probably won't get asked this question very often, but this question has been asked in interviews. So if you went through the thought process and tried to figure it out, I'm sure you gained a lot of valuable experience, even if you didn't come to this solution. And now that you know the solution, challenge yourself. Try and find other problems where you can apply a similar technique of restructuring your data in a way you can use it more intelligently to create faster and better algorithms. And I think that will be very, very valuable. So thank you for joining us today at Coder Inquisition. Good luck.